everyone, and thank you for joining us for the final presentation in this month's Airflow Management Awareness. This is an exciting one. I think you're going to love this one, and it's a great way to wrap the whole session up. And without further ado, I'm going to turn things over to Al Zodos, the president of Upsite Technologies, for a few words and to introduce our speakers.
Thank you, Kennedy. Good morning. My name is Al Zodos. I'm the president of Upsite Technologies. Welcome to today's presentation. This is, as Kennedy mentioned, the last in our series of Airflow Management Awareness Month 2017. Our previous topics for the month in week 1 were Airflow Management 101. In week 2, we covered hot and cold aisle containment. In week 3, the state of the data center and preparing airflow for the digital evolution. If you've missed any of these presentations, we'll have them online. They are online for viewing, and near the end of today's presentation, we'll provide a link where you can access those. Now for today's presentation, which is titled The Importance of Engineering Simulation. Today's speakers will be Lars Strong, our Senior Engineer at Upsite Technologies, and our very, very special guest, Mr. Hassan Moezzi, the CEO of Future Facilities. Future Facilities is the creator of the best-in-class and award-winning Six Sigma DCX suite of software for data centers. At Future Facilities, they develop engineering simulation software, which allows customers to quantify and qualify business decisions while balancing risk against cost. I guess it really comes down to this. Your data centers are typically very dynamic environments, so why guess how changes impact your facility when you can actually know? I know you'll enjoy today's discussion, so without further delay, I'll turn the call over to Lars and Hassan.
So, Lars?
Yes, happy to be here with you, Hassan. We have the virtual facility walkthrough playing now.
Okay. First of all, let me thank you very much, Al, for the introduction, and thank you very much for Upsite inviting us to this presentation. As Lars just mentioned, we're having a walkthrough through a virtual facility. This is the main topic of the presentation today. What you see here is a digital clone of the real physical data center with a lot of details attached to it, which includes the actual assets. The actual details matter. For example, the actual cabinets, the way that they are perforated for cable management. All of these matter as far as airflow, for example, is concerned. The virtual facility is meant to mimic the physics of the real facility. And it's meant to be a sandbox for decision making as far as operational planning is concerned. But more importantly, in the beginning of it, it's used for design purposes. In the area of design, using engineering simulation has been prevalent for a number of years now, and it's pretty standard practice for consultancies and engineering consultants who are designing and constructing these data centers. However, for operational purposes, the virtual facility is a unique concept. It's a new methodology. What you see here, for example, is the actual physics that occurs. It looks like a sort of a poor CGI type of animation, but actually it catches the mathematical essence of the physics of the data center itself. We've tried to include everything from cold aisle containment to underfloor pressurized systems to overhead cabling, etc. A real data center, what you see in front of you. Now, as far as this presentation is concerned, what we want to really focus on is the problems that an owner-operator will face. And the problems that an owner-operator faces is actually in operations, of course, not design. But let's start off with sort of the design aspects of it. So Lars, can I ask you please to go to the next slide?
Yeah, and I want to highlight something that you said there, Hassan, is that CFD modeling has been widely used for the design of new facilities and testing out concepts, but not so much in the operation of data centers. And I want to make sure that people don't miss that point, because I think it really is the takeaway, and the thing to benefit from this presentation is we're going to share a lot of reasons why it's valuable for operations, But it hasn't been nearly widely utilized for operations as much as it could be, and the benefits of it for operations have not been realized. I'm seeing a little bit of a shift as I visit facilities, but still there's a lot of room there, and I want to make sure that that's clear. You'd agree, right?
Absolutely. And there is one thing that I perhaps missed, and this is important. CFD modeling, as you mentioned, Lars, has been pretty prevalent in the design sector of the industry itself. But what has been missing from CFD modeling is the actual calibration issues that go with a real data center. So in design, it's relatively easy to use CFD modeling, or what we call engineering simulation, which is beyond CFD alone. It's very easy to do qualitative analysis of different designs, and that's a very, very powerful technique to use. But when it comes to when the tire meets the road, when you have the real data center, the model really has little value unless it matches the physics of the actual data center in question.
Yeah,
and
absolutely.
That is really where what we find is that the market doesn't necessarily appreciate the necessity for that. And there is a cost associated with it, of course, but we can talk about that later. Please
Yeah,
go ahead, Lars.
yeah, very good.
So what we as virtual facilities are advocating is the use of what you saw at the virtual facility as a decision engine for cost-effective physical design, but also, more important than that, operational planning of data centers. This is a radical move. This is quite controversial. Nobody at the moment is actually advocating that quite yet. But we are starting to get traction with owner-operators who are seeing the benefits of this. So please, next slide. The data center performance. This is a very complex issue. People keep talking about PUE as a data center performance indicator. And PUE is a very simplistic and actually misleading number, even though it's useful in certain ways. What really means performance means from a data center point of view as an owner-operator is to provide IT resilience in running applications at the lowest possible cost at all times. So design of a data center has very little to do with this once it comes to operations. If you click again, Lars, on the next. So in other words, what an owner-operator has got to do to maximize this is to minimize the resources. And the resources we're talking about from a physical data center point of view are really three: space, power, and cooling. To utilize this as effectively as possible at the minimum level, making sure that the resilience is always there as far as the applications are concerned. That's, I suppose, a complicated way of explaining what performance is. As I said, unfortunately, it is not PUE. PUE is only an energy indicator, energy efficiency indicator, important one, but not as important as resilience to most users, owner-operators, or capacity utilization, which is by far the most expensive part of a physical data center.
Yeah, absolutely. And I'll add to that just that there's obviously a lot of focus at operating data centers to reduce their PUE and to demonstrate what their PUE is. And I don't see enough effort digging into the components to find out whether or not they've done all they can at each component level, and particularly the mechanical cooling and the airflow associated with that mechanical cooling is where I see the most opportunity left on the table.
Absolutely. So to start with, let's look at resilience issues. So there are two sections of the presentation. One is tackling resilience using the virtual facility, and then energy efficiency, which is something that everybody sort of recognizes. But resilience is far more intangible. It's very dangerous. It's the most expensive, almost certainly, but also at the same time invisible to most operators. So let's look at the design side from a virtual facility point of view. This is, let's say, as an owner-operator, you press the button and you want to design a new small data center around about 80 kilowatts. We've deliberately exaggerated it by creating a very small data center. It's a pressurized flow void system, and the engineering company in charge has come up with the standard hot out, cold out scenario. As you see, single air handler pressurizing the flow void with the tiles. And what you see here is the guidelines that have come up with 6.5 kilowatts per cabinet at assumption of 120 CFM of cooling required per kilowatt of those cabinets. This is pretty much prevalent throughout the design industry, where the truth of it is the engineering consultancy company doesn't have a clue what the owner-operator is going to do in the data center. In fact, if you ask the owner-operator what they're going to lay inside the data center in the first day one, let alone 5 years down the line, the chances are they don't know that. So the engineering consultancy company has no choice but to go with assumptions. And this assumption is a reasonable one, hypothetically a realistic one, but it is very, very strict. And let me emphasize that. This is a very, very strict assumption. In other words, it's a snapshot in time that if you lay out 12 cabinets you see in front of your eyes at 6.5 kilowatts each, evenly distributed in each cabinet. I'm not sure how many U's it is occupying, but you can see evenly distributed power and the cooling, and everything is hunky-dory. Everything is green, and there's perfect blanking going on. All the rules have been followed. If you click again, please, Lars. What you see here is the simulation results for that particular design. Very straightforward, airflow coming through the air handler, pressurizing the floor through the actual tiles into the inlets in the cold aisles, exhausted through in the hot aisles, and so on and so forth. Very straightforward, standard design. But actually, this is not where things start to go wrong. The minute this room is commissioned to the owner-operator, they will start to change the goalposts. And this is where you start to fragment the space, power, and cooling. And this is where you start to affect performance of the data center. The best way for us to explain that, I mean, for me anyway, is an abstract idea of using the game of Tetris. So please, Lars, if you could click again on the slide. Click again, please, yes. So the game of Tetris, I'm sure most of you are familiar with. And on the left-hand side, you see the perfect design. In other words, you got blocks of squares filling in the voids, and it is complete. But in the real operational sense, the right-hand side is what's happening. You're getting the odd shapes, and those odd shapes create voids. And those voids are basically what we call fragmentation of space, power, and cooling. It's a nice way of trying to say that your problems occur not in design, your problems occur in operations. That's where you start to feel the heat, literally. Now, fragmentation of space and power is relatively straightforward to obviously predict, to see, you control it. And let's go to the next slide, Lars, because we're now going to be looking at the concepts of using the virtual facility for operations. And what we want to show you is, again, the same small data center in operation. And I'm going to take a snapshot of operation at some time down the line. So if you click again, Lars, the same room, the original cabinets have gone out, and the owner-operator is trying to put in this set of equipment. They're completely different from the original design concepts of 6.5 kilowatts per cabinet. They are realistic equipment now. They are not hypothetical. And yet, from a power and space point of view, they have been laid out fine. There's no question that there's enough power to be able to run these pieces of equipment, to run the applications, and also from a space point of view, it's been allocated correctly. The problem that you see in front of you is that 3 of those cabinets have suddenly overheated. Now, what I'm saying is, as far as the fragmentation of space and power is concerned, that's controllable, that's measurable, that's quantifiable. Unfortunately, the fragmentation of cooling is impossible to predict, mainly because cooling is dominated by airflow, and airflow is invisible. So when you fragment airflow, the complexity of the situation, the physics of it, is impossible to predict unless you calculate it. So if you click again, please, Lars, we'll see why those 3 cabinets are overheating. This is sort of a visual way of showing you the complexity of the airflow in that particular setup. Now, I don't want to go into the details of it, but if you do this in a virtual facility and you see it up front, you can actually mitigate this problem occurring. So the virtual facility explains to you why you're going to have a problem and potentially how you may be able to solve it. And in this case, what we have come up with, if you click again, Lars, is actually rearranging the order of the equipment itself. And in this case, again, I don't want to go through the processes that you can go through, but the virtual facility can give you a combination that actually will not create any risk as far as the operation is concerned. All the equipments are green. That means you're safe. So this is one way of using the virtual facility for operational planning. Again, the major part of the fragmentation and the major risk to your equipment is the airflow. The fragmentation of the airflow causes problems, and they will occur at a micro level as well as a macro level. This particular example shows the effect at the macro level, but we've added one slide, which is actually very prevalent to upside as well. The next one shows the actual micro environment of a typical situation in a data center. This is something that happens quite often. Airflow recirculating in front of a cabinet, affecting potentially one or two pieces of kit that could be critical, mission critical piece of kit. And it's impossible for anybody to be able to see this during day-to-day operation without being able to calculate it up front. And on the left-hand side, of course, you see the smoke test. On the right-hand side, you see the simulation itself. These slides where this was done actually by Binghamton University as part of the ES2 project, which is the National Science Foundation research project that's been going on for some years. And they've actually pointed out the complexity of the airflow and how important it is to be able to manage it throughout the operations of a data center for longevity purposes, as well as we will talk about it from energy management point of view. So Lars, do you want to maybe comment on your experience as far as the airflow and the type of things that we're showing here is concerned?
Yeah, absolutely. I think one of the really important things to point out here is that this is a room where everything has been done very well. So best practices have been employed in all cases. We have blanking panels filling all open spaces. And if people will note, there's 2 full rows of supply tiles as well as doors on the end of the cold aisle. So this is a contained aisle, and yet it still is suffering from this one last gap in that vertical plane at the intake of servers. So it doesn't have to be a very large space. I've seen just an inch or 3/4 of an inch under cabinets, allowing warm air from the hot aisle to pass underneath the cabinets and cause problems at the bottoms of the cabinets. And so the engineering simulation is such a valuable way to identify this and to see what the benefits will be once it's solved, once this opening is blocked off. And another really useful tool is obviously an infrared camera. In an operating data center, some of these things can be found with an infrared camera, and not just looking at the tops of cabinets for the warm spots, but sometimes the warmest intake temperatures at the bottom of the cabinet.
Absolutely. The key here, actually, Lars, and you mentioned, you talk about, we're looking at problems here, but the idea that we're pushing as far as the virtual facility is concerned is to avoid these problems. In other words, by predicting it, the engineering cause and effect of the workflow deployment, you can actually avoid this. Usually, future facilities, we get called in when the customer has actually already got problems, too late in the day. And okay, we're happy to help, but that's really not the point of this presentation. The presentation here is really to focus on the fact that you can avoid this and you can quantify this prior to the action itself. But as Lars said, this is something very complex, impossible to predict without calculating it, and impossible to really avoid, because the owner-operator will change the goalposts as time goes on.
Yeah, and I'd like to go back to something you said at the beginning about you mentioned just casually, quickly, that you do the modeling and the software is created in a way that allows you to model the details. And I come, in the industry, I come across people that either love CFD or they hate it. And we all know that CFD is a great example of garbage in, garbage out. Um, and if you don't model the details well, then the model is not going to give you good results. And this is a perfect example of that. If you just assume so a modeler plunks down cabinets on the floor and they don't model that 1.5-inch gap under the cabinets, then obviously the model is not going to reveal what's going to actually happen in the real world. So really important to be able to have the capacity for that detailed modeling and to model all those details appropriately. And that becomes, it's not just a science. There's a little bit of an art to that, but important to have the capability.
Absolutely. You're right. Calibration is really what you're pointing to, Lars, here. And that's really what is perhaps the difficult part, but that is a necessary part of it.
Absolutely.
So, if we go to the next slide, it's the second part of the presentation, really, which is using the same concept of the virtual facility engineering simulation. At the heart of it, of course, is CFD technology, but we're very careful not to call it pure CFD because it involves a lot of other engineering factors in this. But the impact of airflow on energy efficiency. Now, this is close to the heart of a lot of management. I want to see my PUE drop, and I want to see energy efficiency. I want to save money. But let me just emphasize something. When you look at energy efficiency, and we will look at it in a minute, energy efficiency in comparison to a lost capacity, available capacity that's basically being lost due to fragmentation that we're talked about, is a drop in the ocean. Uptime Institute has got some calculators that allow you to do this, and we're talking about orders of magnitude here. So our experience, based on relatively, I wouldn't say old data centers, I would say 5, 7, 10 years old maximum data centers, is that at best, the utilization is about maybe 70%. The owner-operators have either over-engineered in order to safeguard the IT and applications, or potentially are scared of putting any more kit because of localized overheating. Again, mainly dominated by heat, but sometimes they run out of power. What we're talking about is optimizing the utilization of the resources, as we said in the beginning. But let's move on to a real case study, which we're allowed to now display, because this was done, this is work that we've been doing with Citigroup over in New York, and we were given permission to present this. Well, actually, Citi presented this at DCD in March of this year over in New York. And this was a very important project because it was groundbreaking, because NYSERDA, for people who don't know, NYSERDA is a New York State sort of body that actually provides tax breaks to facility managers in New York State to encourage them to provide energy efficiency changes to their facilities. In this case, for the first time ever, NYSERDA accepted that simulation techniques like ours, a virtual facility, can help reduce the energy consumption by allowing Citigroup to avoid risks to their IT equipment. Because it's very easy to keep talking about raising temperatures because Intel says you can do that, or ASHRAE says you can do that. But Citi, being very, very risk averse, will not allow this to happen without the IT department being absolutely certain that raising temperature in the room is not going to affect their applications. That is absolutely critical. So using the virtual facility, we were able to cover all three grounds: utilization of capacity, risk management, of course, which is the first top most important thing, and finally the energy efficiency. What you see in front of you is the real data center in all this detail. It's 3,400, it's about 40,000 square feet. And the goal was to demonstrate that this to NYSERDA was to actually demonstrate that you can use this technique in order to reduce the energy efficiency, increasing energy efficiency in existing data centers without having to buy a new facility or build a new facility. By the way, one other thing, it's important, energy efficiency as far as NYSERDA is concerned is very straightforward. You just look at numbers of utility bills. But in reality, the question we raised with NYSERDA is, what if city could continue using this particular facility for another 3-4 years, rather than having to build a brand new one with fancy new technology built into it? Wouldn't that actually be a better savings of energy? And that actually made a lot of sense to them. So if we go to the next slide, please. You can see the details of this data center. This was a calibrated data center, by the way. As big as it was actually measured, calibrated. It's in New York City. 78% of the space was used. 53% of the 2.2 megawatts was used. 100% of the CFM was continuously used. As far as cooling is concerned, the PUE was about 1.8, which was not great, but wasn't not untypical. Environmental performance was not great because they did have hotspots, which concerned them a lot, and they didn't understand it. And this facility still supports migration as far as cities concerned. Sorry, please go ahead, Lars. When we ran the calculations, very similar to what we showed you earlier on, the first goal, and this is you can see the presentation from TCD anyway, but the goals were actually, can we do the energy efficiency going after the lowest hanging fruits first and then increasingly going to more difficult parts. So non-invasive, the first priority was non-invasive, no cost or low cost with available stock available at City, changing of floor grills, blocking of the gaps in the floor, cabinet blanking, of course, the sort of thing that Upside is obviously focused on. And by doing the simulation, we could point to exactly where they should do this. That is going to have the best effect as far as the room is concerned. So we did everything that you see on the right-hand side for item 1. And number 2, some of the cabinets, for example, had fan trays that were temperature controlled. We actually had to optimize individual fan trays and set new temperatures, sensors to new temperature controls in order to be able to optimize the airflow through the cabinets, as well as effects that they have on neighboring cabinets as well. These were all done following the full calibration of the data center and actually running of the simulations for different scenarios. Lars, this is much more Upside's type of solution provisions for customers. Perhaps you may want to sort of comment on the sort of things that we're talking about, grill movements, the fan trays and cabinets and blanking, etc.
Yeah, I think the interesting point is being revealed here is that it takes something as sophisticated as this engineering simulation that you're doing and the calibration of that simulation, along with the very fundamentals of airflow management, the sealing of cable openings and blanking panels. It takes a combination to achieve high efficiency in a facility. And a lot of people are focusing on containment solutions and advanced cooling solutions and airside, waterside economization of various sorts, but without the addressing the basics, nothing's going to get as far as it could. The efficiency is not going to go as far as it could if the basics are included.
You're absolutely right. And I suppose the way I look at it is very simplistic. You have a massive data center like you have here, 40,000 square foot data center. You have a massive plant that's supplying the cooling to the entire white space. Imagine that plant has got to deliver enough CFM, the right temperature, right relative humidity to every single piece of kit you're talking about thousands of them sitting in the data center.
Yeah.
And each one of those pieces of kit could have different configurations. I mean, as far as they're concerned, it could have different tolerances. And this is the job of the facility manager, the owner-operator. This is a very tall order. And that's why, at least by doing a virtual facility, you have visibility. You see exactly what's happening. And there may be some issues that are not solvable as far as the situation is concerned. So you may have to take drastic action. But what we see in the real world of the data centers that we visit is there's a hell of a lot of wasted resources, enormous amounts, that can easily be addressed if you shine a light on the data center itself.
Yeah,
So,
and that was really, sorry to interrupt, that was really highlighted by your previous slide where you we're only at a 50-some% of the power capacity, but 100% of the airflow capacity, and they still had problems.
correct.
Because it wasn't a capacity problem, it was a management of resources problem.
Absolutely, absolutely correct. So,
yeah.
So if we go to the next slide, so that's 1 and 2 priorities, and then 3 and 4 will basically, as it becomes more expensive, to partial side panels from network frames, custom blanking, cabinet shelves. I mean, we did a whole lot, and it's ongoing, by the way, as we speak. And then the final part, the 4th one, is cabinet change. These are the most difficult because here now you're talking about moving equipment from one location to another. And as you all know, that's a very difficult task for IT to actually implement. If you're asking them to move, I don't know, a Cisco network from one place to another because of its, the risk, the inherent risk that it's facing. So that was left to the end, and sometimes you have to do that. So these were the steps that came out of the baseline report that we provided, and as we speak, it's being implemented. So if we go to the next slide, this is the sort of thing that really Upside is tooled out to do. So the simulations themselves showed on the left-hand side, we're talking about the complex open rack situations where you got the side-to-side cooling, which is the biggest problem for headache for most owner-operators. And this is not going to change. The hardware companies will have their own rules as far as the design, the form factors, and the cooling systems for the boxes are concerned. And they will hand out, big, thick, manuals to say the onus is on the owner-operator to provide the right environment for their piece of kit. And these kits are very expensive, and of course they run even far more expensive applications sometimes. So what you see here is a typical situation that occurs in data centers all over the world. Side-to-side cooling creating hotspots. And if you look at the temperatures on the left-hand side, this is the baseline model. And you can see the red, basically meaning that it is pretty much near overheat. It's survivable, but it's not desirable. On the right-hand side, it's the remedies. Very cheap, very low cost. We're talking about blanking panels and so on and so forth. But in the appropriate position. There's no point in just blanking for the sake of blanking. You need to do it in the right way for the right reasons. And that's why this type of simulation, hand in hand with the physical implementation of the blanking, is the most optimal way of moving forward. So post-optimization, you can see all the temperatures dropping to green or yellow. And that allows, of course, raising the temperatures and therefore energy efficiency measures that can go hand in hand with it. So please, if we go to the next slide. Lars.
Yeah.
So you may want to comment on that as well, if you wish.
Well, yeah, there's one thing to add there is the concept of raising temperatures is a little bit controversial. It gets people pretty worked up about it. But there's a really important distinction to be made, is the difference between what are we talking about, raising the temperatures of the supply air or the intake temperatures of the IT equipment. And a lot of people think that they're perfectly linked, that if you raise the supply temperature of the conditioned air, then you raise the intake temperature of the IT equipment. That's true if you don't make any changes in the computer room. But what's possible, as you're demonstrating here, is that by making improvements to how the air is managed in the room, then you're able to reduce temperatures in the first place, get rid of some hot spots, giving you room to raise supply temperatures and realize those efficiency improvements without, in the end case, causing higher intake temperatures to the IT equipment. And in some cases, they're actually lower. The hot spots have gone away, and you've raised supply temperatures. And so really important to have that conversation at that level to break out the different components.
To that point, actually, let me highlight one of the cases we've done over the years. We were called into a particularly difficult situation for one of the major banks, where mission critical rooms were at only 45% of IT power load, and they had alarms, thermal alarms going off in several cabinets within those data halls. And in that case, it was the facility manager who actually was following all the rules exactly as if he was deemed to do. He was delivering the cold aisle air at the right temperature, X-ray temperatures, everything was abided by in front of the cabinets. And he was delivering the power and the cooling to where he had to. The problem was he had no control internal to the cabinets, inside the cabinets. The cabinets were obviously laid out internally by the IT department. But the IT department was demanding that the alarms are going to be basically switched off. And the facility managers had to do this, literally via lowering the temperature of the room. In other words, the energy, they had to lower the supply temperature to 11 degrees centigrade. That meant enormous losses in energy efficiency. So you're absolutely right. The room temperature does not necessarily have a direct link to the inlet temperatures of the individual pieces of kit, which is really where the alarms start to sound off. And that's something, again, goes to the complexity of the airflow. There's no good trying to abide by the ASHRAE in the corridors at 2/3 of the height of the cabinet, 40 centimeters from whatever the measure is. That's really not going to do the trick. What matters is what actually enters the individual inlet situation as far as each one of those pieces of IT kit is concerned. Whether that inlet is on the side or it's on the front, it doesn't matter. So this particular picture that you see here is another one of the highlights of the changes that we did at City, whereby this is, I think, a Cisco 9513 system where the inlet and the exhaust are on the same side, I believe. I may be corrected here. But what you have is a situation where Cisco basically designs it the way it is. It's up to you to manage it. And what we had to do, we came up with new not blanking, but
baffling systems,
baffling systems that actually creates a very much more acceptable situation. And you can see the airflow changing quite dramatically, and the inlets, the temperature inlets, were dropped considerably by 20 degrees or more in this particular situation. Again, going back to what you said, Lars, allowing the room for maneuver as far as the raising of the temperature and energy efficiency is concerned. Without this, there's no way City would have allowed raising of the temperature as far as this is concerned. Sorry, Lars, you may want to add to that.
Oh yeah, absolutely. Just a very clear point. And for those that are Fahrenheit focused, 11 degrees C is just like 52 degrees Fahrenheit. And it's still not uncommon for me to find supply temperatures in data centers in the 50s, the high 50s, the low 60s, which is extraordinarily cold, extraordinarily below what ASHRAE suggests is a minimum intake temperature of 64 degrees.
Correct.
Yeah.
So I suppose the pièce de résistance is the next slide, Lars, which is really the results.
Yeah.
So the airflow, we reduced the airflow. We switched off basically some of the fans or reduced the fan flow rates. I'm not the person who did the work, so I won't be able to. I may stand corrected. But basically, the bulk numbers are the CFM, the total CFM supply went down from 722,000 to 541,000, and we managed to raise the temperature by 5 degrees Fahrenheit for the chilled water system itself. This, of course, then led to the savings you see on the next slide. First of all, the power utilization. What you see is the power utilization, as far as the lighting is a very small amount of the miscellaneous is the same as before. Chiller plant load is pretty much the same as before. But what actually has changed dramatically is the power utilization. In fact, the power utilization for the fans has reduced dramatically, and the IT load has gone up. That's where the efficiency gains have been. Sorry.
Absolutely, and I think that's probably quite conservative. I would imagine that there were some significant chiller plant efficiencies as a result of raising that chilled water temperature. So
yes,
I would take this as a conservative demonstration. And
basically, the next slide is what a lot of people measure the performance of the data center, which we said earlier on in the presentation. The PUE reduction, it was over 1.8. It is now below 1.7, and that certainly is going to perhaps improve later on. But the next slide shows the dollars and cents savings that was made. So the cost saving, the total estimated cost saving per year for that one site was about $403K per year. The total cost of implementing these very cheap, low-cost, fixes is only about under $30K. So this is baffling, etc. That we're talking about. Again, the strategic positioning of those baffles is a critical part of it, not just the baffling itself, which is necessary, but this is just how you do it, where you do it, and so on and so forth.
Yeah.
So that's together. I think the next slide perhaps I'll sort of pass it on to Lars, but I'm going to stop at this stage. This was a real case study which we're allowed to talk about. It is an ongoing, and let me also emphasize, the Citigroup is now planning to roll this out slowly but surely to various mission-critical sites around their operations around the world, and of course the U.S. being the main starting point. And I'll leave that with you, Lars, if there's any questions from your side, or you want to comment on your side as well.
Yeah, well, thank you very much. I think those are some very clear examples, and it's really nice to have the videos and the graphics to demonstrate for people what the changes are that are happening in the rooms. It's just amazing to watch people's eyes light up when you make the invisible visible through the engineering simulation. So we're getting close here to the end of this webinar, and I want to encourage people to ask us questions. I've got just a couple more things to share, and so I encourage people to dig into this and ask questions about what might be happening at your site, or something we've perhaps not been clear about. Would appreciate that, and we're available for that in just a couple moments. I want to share just this real simple concept of what we're calling the 4 R's of airflow management. It gives people a way to get their hands on the process. Airflow management improvements, improving airflow management, it's not an event, it's a process. It's an ongoing process, and it's somewhat iterative. And by looking at it in these 4 different chunks, the rack, the row, the raised floor, and the room, gives people something to really dig into, and people at sites can make an effort to improve the airflow management of the rack. Just really look at that vertical plane across the intakes of equipment and say, what can I do to improve that? Obviously, blanking panels, not so obvious, the gaps under cabinets, filling gaps between cabinets, and then once an effort has been made to improve airflow management at one of these levels, the little arrows that curve into the room level remind people that it's necessary to go look at the controls and the set points to realize the benefits. airflow management improvements don't actually save money. They create the environment where money can be saved. So as Hassan detailed, they modeled the city site, they found lots of problems, and then they addressed them. They were able to use the simulation to identify whether their predicted solutions were going to work or not. And once they were implemented, they were in a position that they were able to turn down fan speeds and raise the chilled water temperature, raise the set point temperature of the conditioned air. And so after making these improvements, it's necessary to look at the controls to really realize that benefit. We've produced a short video in conjunction with Future Facilities to demonstrate this. It's a short 4-minute video about the 4 R's and the process of improving airflow management. While it's for day-to-day operators, it might be pretty obvious, but it puts it together in a really nice way that can really communicate to your superiors or others in your business that aren't familiar with these concepts how the whole process works. So a lot of people have been saying how valuable that is a tool. Here are just listed the different elements of the 4 R's for your reference. If you take a look at this webinar later and you want to see this slide and explain it to somebody else, here's what those 4 R's are. I want to take just a moment to step away from the educational aspect of what these webinars primarily are to share with you a little bit about the product sets that we've developed to improve airflow management and address all these holes. We're always looking for holes in our product line to fill, pun intended, of course. Where are the holes in the data center that there's no solution for? And these are the 4 families of products that we have to address that horizontal plane of the raised floor. We have the cold lock line, a wide variety of products. We have a new one that is now a 5-inch square grommet that we're seeing a shift from larger openings in the raised floor to smaller and smaller openings as more cabling and goes overhead. So we've made a smaller grommet to address that. In the rack line, the hot lock line of products, we have a new product called the Switch Fix, which ducts air from the face of cabinets back to either side intake or front intake switches that are often mounted on the back rails of cabinets. And these have been very problematic for a lot of people trying to improve the efficiency. Then, of course, our aisle lock line of products to address airflow management at the row level. All of these attach magnetically and are just extraordinarily simple and flexible for changing environments. They can be installed in a room that is under the process of getting improved. So for example, at City, these aisle lock products could be purchased day 1 to make improvements, and then as cabinets are rearranged and things are shifted into more hot cold aisle alignment and cabinets or gaps between cabinets are closed, then the containment can flex along with those changes in the room. And then we have our energy lock line of products is wired and wireless monitoring with a wide range of sensing capabilities of different sensors with industry best leak detection sensing rope. So always looking for ways to address and help everybody to get to the goals, get to the reduced PUE, get to the efficiency goals that they're looking for, as well as recovering the stranded capacity just to get more out of the site, as Hassan also mentioned in his presentation. So with that, we're about to wrap up. I want to let everybody know that all these videos, all these webinars have been recorded and are available on our website. Here's our contact information. We're both very happy to have any continuing dialogues, answer any questions offline that we're not able to address right now, but I want to open it up for any questions that people have.
All right, thank you, Lars. Yeah, we've got a few questions here. The first one is, if the load in the data center is dynamic, changing, how can calibration work? Same goes if the cooling varies, such as airside economizer throughout the day.
Okay, so I'm going to answer that from the virtual facility. I'm actually not the right person to ask you technically, but we handle exactly those situations. As far as the calibration is concerned, obviously, we instrument the room itself from a temperature measurement point of view over a period of time. As far as airflow measurements are concerned, we take barometer readings if it's tiles that the pressurized floor void, and we balance and calibrate the room accordingly. Of course, there will be variations, but we have ways of calibrating that. I'm quite happy to discuss how we do that as far as the answer to the question is concerned. But it is absolutely necessary to do the calibration before moving on forward. There's no way we would actually recommend improvements to the room unless we actually do the modeling and the calibration to some extent before we make decisions. But in answer to the question, I'd be more than happy to introduce you to our engineers in order to explain how the balancing is done and the calibration is done with variable power as well as variable control systems on the cooling system.
Right.
Yeah, and I'll add a little bit more. It's a very good question. It's often used as a way to say that engineering simulation breaks down or doesn't work because it can't handle these things. But what it points to is that without these tools, a lot of resources have to be thrown at the problem. And so this comes up in containment, and as the person asking said, what about economization? Well, it comes down to the ratio of the supplied air to the IT demand air, and absolutely, IT equipment has varying demands for airflow. It spins up and sucks in more air, requires more cooling at times than others. And so without these tools and without sophisticated like monitoring and controls, you just simply have to throw more air at it all the time than it needs. You have to meet its highest demand, as it were. And then the other times you're just wasting and being inefficient. So with better management of the resources and increasing levels of monitoring and controls, then it can be more and more right-sized, or can be more and more matched to the demand. And and in each situation it gets complicated. Yeah, go ahead, Hassan.
No, just let me add something perhaps to put the gentleman, whoever has asked the question of these. We actually model in our virtual facility, we model the control systems, the variability of the control systems. That is taken into account. The question is absolutely correct. If you have variability in power demand as well as the airflow, the FDs, etc., we actually model that. Because without modeling the control systems, you're not going to get the right answers. Yeah. So again, I'm quite happy for us, our engineers, to talk to how we do it, and we can show you some of the examples we've done it. We've covered all types of data centers. We're totally agnostic about the way the cooling is supplied to the room itself.
Yeah. All right, awesome. So one other question we've got is, our data center is a bit on the older side. Would a system like this still help us?
Absolutely. Quite often, we get confronted with a situation where the data center is seen to be at the end of its life because they've got hotspots and so many problems and problematic. And the customers are the owner operator is thinking of abandoning the data center, shutting it down, buying a new site, or building a new site, or leasing a new site. And we go in there, we model the site, we actually show them that by actually doing some very low cost adjustments to the room itself, they can actually improve the longevity And you could save millions. I'm not talking about small amounts of money here. We're not talking about energy savings here. We're talking about years, extra years, 2 years, 3 years of longevity, because a lot of it's really lost capacity. It's stranded capacity, if you want. We actually retrieve some of it, not all of it, but some of it. And we do that on a continuous basis. Again, let me emphasize, it's too late when you get to that stage. What we're suggesting is using this technique, you can actually see it happening, and you can adjust your operations accordingly. And one last point about this. We have come across situations where older data centers have not been designed for, let's say, more than 100 watts per square foot, or 1,000 watts per square meter, or something like that. And suddenly, this new monster of a machine is coming in at 30 kilowatts with a very small footprint. And they start to be very scared. The owner-operator gets scared. So the technique allows you to adjust for accommodating these anomalies at any point in time. Now, it may be you're not going to get a free lunch here. You're going to have to adjust your cooling system in order to be able to address that. But you can do it in the most efficient manner. And we do that on a continuous basis for different customers. So let me stop there.
Great, awesome. Probably got time for one last question real quick. How much does it cost to build a virtual facility?
That's an important question. It is, to build the model itself is not really that expensive. But again, it depends on the size and the details that you need to go into it. But the calibration is really the important thing. And the cost of it, depends on the amount of data that you need to collect and the amount of time you spend on site. But typically, let's say if you have a 5,000 to 10,000 square foot data center, which is not a very big one in the US, but in Europe and Far East is typical size, we are talking about expenditures from the beginning to the end of about, say, 6 weeks of elapsed time with the right amount of data available, costing the customer around about $30,000 to $40,000 to actually build and calibrate the data center. I don't want to stick to that number. There may be some variations in that, depending on the availability of the data and how easy it is to be able to measure stuff. But that's typically the way to build the model. And then there's ongoing licensing costs that, if they adopt it for operational planning, that gets lower because of, again, it's going to be dependent on the size of the data center and the location of it and so on and so forth. But we can always provide numbers to various people who want to know that.
Great, yeah, they can reach out to you and you get them in touch with somebody on
Absolutely.
your team. Yeah.
Correct.
All right, everybody, that's pretty much all the time we've got. This has been the June Airflow Management Awareness Month. It's been a really great time. We appreciate, Hassan, you're helping us out with this final presentation. I'd like to thank everybody for attending and remind you again, all of these can be seen on our website at any time. Just go to the main page, upsite.com. There's a button right at the top there that will take you to the page where you can view any of these recorded sessions. And we look forward to doing more of these webinars and, of course, towards doing Airflow Management Awareness Month next year, 2018. But we would like to remind you that though we declare June as Airflow Management Awareness Month, airflow management should be at the top of your mind all year round. Thank you again, everybody. Have a great day, and we will talk to you soon.